Hey, what's up guys? Welcome back to another video in the Deep Learning with Tensorflow series. In this video, we're going to build a neural network for single label multi-class classification. Welcome back everybody. So previously in the last part, we did something called binary classification. Basically what this means is that we're making a machine learning model, or specifically a neural network in our case, to predict whether a sample is either class A or class B. In our example, it was negative or positive. So that's only two options, but in the real world, sometimes you have a lot of options. That would be multi-class classification, which you can actually break down further into single label multi-class classification and also multi-label multi-class classification. So these sound very similar, but they fall under multi-class classification. So basically what this means is that you have, instead of only two classes available to you, like negative or positive, you have multiple. So this could be like dog, cat, goat, zebra, and so on, okay? So you just simply have more than two options. So with single label classification specifically, you're just choosing one of these multiple options. So this would be like only dog. And then with multi-label, multi-class classification, it could be like dog and cat. So basically you're identifying it as part of multiple classes, okay? So we're going to focus on single label multi-class classification. And one of the best data sets for doing that, just like before, it's part of TensorFlow inside of Keras, inside of datasets, import Reuters. So the Reuters dataset, I believe Reuters is like a newspaper or just like a news agency or whatever it's called. So I just looked it up, and this is a more detailed description of what it is. So basically, it's a dataset that has about 11,000 news wires from Reuters, and they're labeled over 46 topics. So on the topic of multi-class classification, the classes that we have in terms of how many there are is 46. We have 46 different options. And so the whole point of this data set is to make a machine learning model that can predict each sample as being part of one of those 46 classes, okay? So these classes represent topics like, I guess, politics, science, economy, stuff like that, okay? So hopefully the actual problem that we're trying to make a model for makes sense. So we can do Reuters.load data. And just like before, same exact concept as before, we want to specify the number of words parameter, which will basically only load in the top 10,000 words, the top 10,000 words that are used the most often, okay? So we'll bring that in now. And then after we bring it in, we'll just go ahead and print out train data.shape to see what it looks like. So we can see that we pretty much almost have 9,000 samples. And then for the test data, let's see how much we have. We have basically 2,200 samples to choose from. And then let's go ahead and print out a single training sample. Let's take a look at what that gives us. Okay, so we can see that it's just a simple Python list of numbers, just like before in the last episode. So before we were classifying IMDb reviews for movies, and this was also given to us as a bunch of numbers. And each of these numbers represents a specific word in the dictionary that has the most common 10,000 words, right? So it's already tokenized for us, meaning that's converted from a text form to numbers in vector form. So then let's also print out the training labels, the first one, and we get 3. So the first sample in our training set is labeled as 3. So whatever that third topic is, that's what it would be, okay? So first things first, the initial problem that we have is we want to pre-process our training data to make it so that all of the vectors representing each of the Reuters news articles is the same length. Because again, a neural network expects inputs of consistent length. They have to be the same length each time, okay? So we want to make sure that each of the vectors is the same length, and the two different ways that we learned about is either padding or multi-hot encoding. So we'll bring in our multi-hot encoding code again, same exact thing as before. So we're just calling that function on the training set and then also the test set, and then we'll just do that. Also, the benefit of doing this is not only is it multi-hot encoding it, but it's converting it into a NumPy array so that it's formatted a little bit better, it's shaped better, so we can see that there's roughly 9,000 samples, and then for each sample we have a vector of 10,000 in shape, or size rather. So that is vectorizing our input just to make sure they're all the same length so we can feed it into our neural network. Now what we have to do is decide whether we want to encode our labels. So we saw before that our labels are just integer numbers, so that represents the class that it's labeled as. So in the last episode, we had to do a few things to transform our training data into a form that is proper for neural networks. Specifically, what had to be done is that each review that's in the dataset had to be translated into numbers using a dictionary, which is already done for us, which is very nice. But then we had to do the extra step of making every vector the same size by either doing padding or multi-hot encoding. But now with this particular problem with single label multi-hot encoding, we have a label, and this can be any number, and each of those numbers represents a single class in our set of classes that we can choose from. And what we need to do is decide how we're going to encode those labels. Currently, they're just numbers, like I said. So, like 0, 1, 2, 3, 4, 5. We actually have to make a choice. Do we want to leave it as integers, as it is currently, or do we want to do something called one hot encoding? I've got this visualization here that shows what one hot encoding is, how to do it. So what we've got is a single label multi-class classification problem. So this means we have multiple classes and we're trying to choose one of the classes to label each sample, okay? So let's just imagine for this particular example here that we only have three options: cat, dog, or bird. And so all one hot encoding means is that you're going to have a vector of the same size as however many classes you have, and then each index of the vector will correspond to one of those classes. And this is kind of very similar to the multi-hot encoding that we did last episode, except that the difference here is that we're only choosing one class per vector. But with multi-hot encoding, we had multiple classes selected per vector. So in this particular example here, if our label is supposed to be cat, then the vector for that, the one hot encoded vector, will just be 1, 0, 0. And the first one is 1 because the first index is for cat, is the first class that we have here, okay? And so for dog, it'd be 0, 1, 0 because the second element corresponds to the dog class. And then for bird, it'd obviously be 0, 0, 1. And that's it. That's literally all there is to one hot encoding. It's simply taking the set of all our classes that we have in this problem and making a vector of that size. And then for each sample, whatever class is representing that sample, as the label, then you would have a 1 in that spot, okay? Okay, so now that you guys understand what one hot encoding is, now we can proceed. So in terms of the pros and cons of each approach, the integer format is more memory efficient because with the one hot encoding, you have to have a vector that is the same size as however many classes you have. So if you have 48 classes, you have to have a vector for every single sample that is 48 in length. But with the integer format, you just simply have a number, right? That takes obviously less memory than a vector of 48 in length, right? Another benefit of using the integer format is less preprocessing. Since we're already given the data in this format where the labels are just integers currently, we don't really have to do any extra preprocessing to get it into one hot encoding. Even though it's pretty easy to do, we could just leave it how it is. On the other end, of course, since we have to do one hot encoding, that's going to take more preprocessing just to convert it. In terms of how our model will do when we're training it, it'll do the same amount no matter which encoding format we use. If we want to do integer encoding or one hot encoding, it'll be the same thing. The only thing that will be different is the loss function, which I'll talk about in just a second here. But one of the reasons you may want to use one hot encoding is just because some models or some layers of a model may require it to be in the one hot format. For this specific problem that we're tackling today, you can use either one, it doesn't really matter. I'm specifically going to show you guys one hot encoding just so that you're aware of it and that if you see anyone else use it, you know what it is and how it works. And also in the future, if you come across a situation where you have to use one hot encoding, you'll also be familiar with it as well, okay? Okay, so with all that said, hopefully that all makes sense. Let's just start from the top here. So we have our input labels, and so for those labels, you can choose how they're going to be encoded. So with both of these particular options for how you encode your class labels, you're going to have an output layer on your neural network that has an activation of softmax. That's just the activation that is used with this particular type of problem, just softmax. And last time we used sigmoid, which just outputs a single probability number that represents the probability of it being the positive case of 1. But in this particular problem, we're predicting the chances that the sample could be part of different classes. We only want to choose one class though, right? So basically, the way that this output layer is going to work is instead of outputting one number, it's going to output a vector of numbers, and each of the values of the vector will represent the probability that the sample is a part of that particular class. So just like one hot encoding, the size of this vector will be the same size as the amount of classes we have. So for example, again, if our classes that we have available to us is dog, cat, and goat, then if we feed something into the neural network and it gives us this here, this would be saying that the neural network thinks that it is 0.1% probably a dog, 0.2% a cat, and 0.7 a goat. Obviously 0.7 is the largest one, so we're going to say that the neural network thinks that this particular sample is a goat. That's the same thing if you one hot encode it. And so the last thing I want to tell you guys about is the loss function. So if you do the regular integer encoding, you're going to use a loss function of sparse categorical cross entropy. In the last episode, we learned about binary cross entropy, which is for binary classification problems. But if you use one hot encoding as your label format, you're going to use the loss function of just regular categorical cross entropy. Internally, these are pretty much doing the same thing. They're simply measuring the differences between the output of your neural network, the predictions, and the actual values, same as any loss function. But the specific differences between sparse categorical versus categorical cross entropy is that sparse categorical is specifically for when the output is an integer, and then it'll just know how to take the probabilities that are produced by the output layer and figure out which label is trying to map to, okay? So hopefully that makes sense. And just to summarize in one sentence, if you label your input using the integer format, use sparse categorical cross entropy. And if you label your input using one-hot encoding, use the loss function of categorical cross entropy. All right, so hopefully you guys understand what one-hot encoding is. Now we can put it into practice. So again, it's optional. You don't have to do it just as I described. So basically what we're going to do is use the tensorflow.keras.utils. There's a function inside of this that will automatically do it for us. It's just called toCategorical, because one-hot encoding is also known as categorical encoding, which lines up because we're predicting different categories basically. So yeah, the way it works is we're going to give it our labels. We're just going to feed it into the function, and this will produce a new set of data that has every single label one-hot encoded for us. So just to see what that means, we're going to print out the first sample. So we know that the first one originally was labeled 3. And so now if we just one-hot encode it, we can see that the output is now a NumPy array, which is also great. But also we can see that we have 0, 0, 0, 1, and the 1 is in the third spot. So that makes perfect sense, I think. If the number was like 1, obviously it would be the second one, or index 1, and so on, okay? If you decide to do integer encoding, the only thing that you need to do is just take your labels, your train labels variable, and make sure that you convert each of the samples into a NumPy array, because right now this variable is just a regular Python list. All right, so now we can actually do the fun part. So we can import Keras, and we can actually design our neural network. So we're going to make a new model. We're going to be doing keras.sequential. We're going to go ahead and skip our input layer because we saw that that one is not required. We're going to do our first hidden layer. So we're going to do keras.layers.dense. And now we just want to choose how many neurons we have in our first hidden layer. We're going to do 64, okay? I'll explain that in a second. We're going to have an activation of ReLU. And then we're just going to add on a second hidden layer. You can do however many you want to start with. We just want to get some initial results before we start modifying this. So we're just going to have a second hidden layer with the same number of neurons. And it's also going to have an activation of ReLU. And then we're going to have our output layer, so keras.layers.dense. We learned before that the output will depend on the type of problem that we're doing. In this case, we're doing single label multi-class classification. So the way the output works for that is we want a vector. Output is a vector that has the probabilities that the sample is each class. So we know that there's 46 classes to choose from, so we'll do 46. And then the activation will be softmax. So for the previous problem with binary classification, we did the sigmoid activation. But with this particular problem that we have here, where we're trying to have our output vector with all the probabilities that add up to 1, we're going to do softmax. If you don't understand the whole vector of probabilities thing, then don't worry, I'll show you that in a second, okay? So now that we have defined the layers of our model, we can go ahead and compile it. So model.compile. We're going to pass it our optimizer, which we'll just use the standard atom optimizer. We're going to do our loss. And I told you guys before that the loss will depend on what type of encoding that you do above. So I told you guys before, if you leave it as integer encoding, you're going to use something called sparse categorical cross entropy. But if you do one-hot encoding as we did above, you're just going to use regular categorical cross entropy. Just like always, we can define multiple metrics, but one of the metrics that you can do usually for this particular problem is the accuracy, which is actually the same metric that we mentioned last time, which is the number of correct predictions over the number of total predictions. We're still doing classification in general, so this is still a metric that makes sense for this particular problem. All right, so now we can go ahead and train the model. So we can do history is equal to model.fit. We're going to pass in our training data, our training labels. The number of epochs we'll do initially as 30. We can do a batch size of, we'll do 512, and then we'll do a validation split of 0.2. Okie dokie, the model is done training, so now let's go ahead and plot our results so we can visualize what happened. Here we go, so we've got our training and validation loss plotted versus the epochs. So we can see with our training loss, it starts up very high and then goes down quite rapidly, but still continues to decrease over time, which we expect. That's a sign that your model is learning. And then our validation loss does pretty much the exact same thing. It starts up high, decreases rapidly, slows down, but still decreases. But then at a certain point, you can see that the line starts to trend upwards. So it's very slight, but if you look closely, it is going up. And what we learned before is that that is called overfitting. The model has converged at some point here, meaning that it has generalized the best it can. It learned as much as it can, and then it starts to do better on the training data, but not so much on the new unseen data, okay? We also learned that one of the things that we can do to fight overfitting is cut the model off at the point in which we detect that that occurs. So if we detect that, let's just say it's, I don't know, like epoch 14 or 13, we could stop the training of the model at epoch 13 or 14. And then here's our training and validation accuracy. We can see that the training accuracy gets really, really high, above 90%, almost at 100%, which is awesome. But obviously, we want to focus on the validation accuracy, which we can see coasts just under 0.8%, or 80% rather. And so what you would do at this point is just tweak your model hyperparameters to prevent overfitting and squeeze out the best accuracy and loss you can get from the model. We've talked before about the different things that you can do, like changing the batch size, the actual layers themselves, the number of neurons in them, and how that affects the training process. So, but yeah, now that we have our model, we can go ahead and evaluate on the test set. So we can do results is equal to model dot evaluate, pass in our X test data, and then our X or Y test data. There we go. So now we can see that we have a loss of 1.12 and a accuracy of 0.79, which I basically explained above. It's just under 80%. So let's see what a single output from our model looks like, a single prediction. There we go. So we get this giant vector of all these different numbers here. We can see that they're all very small numbers too, with these exponents here. And like I told you guys before, this is representing all of the probabilities for every single class that we have in our problem, that the single sample that we've selected here is a part of those different classes. So some are going to be higher than others because the model has a higher confidence that the sample that you gave it is part of a particular class. So basically the job of you when you're taking this prediction, or the loss function when it's actually comparing the predictions, will be to go through this vector and choose the one with the highest probability, because that's the one that the model is most sure of. So one way we could do that is by doing np from numpy.argmax, and then we could do predictions 0. So we're taking this vector that we have here, feeding into this numpy array, and this will just output the index that has the highest probability, or the highest number, which is 3. So that actually lines up perfectly, because if you scroll all the way back up, we saw that the first label is 3. That's the actual label that it should be. And so when we scroll back down here, we can see that the index with the highest probability is 3, indicating that that is the actual prediction. So that's really cool to see, honestly. And also something interesting is that they all add up to 1, just like I told you before. So one way you could prove that is by doing np.sum predictions 0, and we get 1.0. So that is how we can make a neural network that can do single label classification. And hopefully that all made sense. The main things that you need to know really is just, like always, the loss function that you're supposed to use for the type of problem that we're doing. In this case, it also depends on the type of encoding that you do for the labels. So if you do one-hot encoding, use categorical. If you do integer encoding, use sparse categorical. But everything else is really just playing with the options. One thing I want to mention about the layout of our neural network is that you notice that the number of neurons that we have in our hidden layers is larger than before, but also larger than the output layer. As a general rule, you should just have your intermediate layers descend in terms of the size of the neurons, but especially have the number of neurons be greater than the output. Because if you don't, if you did something like this is known as an information bottleneck, which you can kind of imagine. So the first layer has 64 neurons, so it's going to try and learn some patterns from the data, extract some features from it. So then it's got to squeeze all of that information into the next layer, which only has 4 neurons. And then that feeds into another layer that has 46 neurons, which is our output. So it has to take a smaller amount of information and extract it into a bigger amount of information, which kind of doesn't really make sense. If you kind of visualize that, that's a bottleneck, right? Going from less information to more information makes less sense than going from more information to less information. So as a general rule, just have your hidden layers feed into your output layer with more neurons than the output layer. In terms of why you would choose 64, you don't have to. I mean, this is just a choice that you make when you first make it, but you can always change it. The idea is that you choose one, and then you see how that performs, and then you change it up or down to see what that does as well, and then you just tweak it, right? We talked about this before, but I'll reiterate that when you have more neurons, this allows you to learn more complex patterns and features in your dataset, which can be good for complex datasets and complex problems, but also the higher amount of neurons that you have, the more overfitting can happen. So there is a correlation between the complexity of your model, which is the number of neurons and layers, and overfitting, okay? So right now, if you just evaluate the model, we see that we have a validation accuracy of about 80%, right, on the test set. So let's just see how changing this will affect that. So first of all, let's make it go up a little bit. We'll do 256, and we'll squeeze that into 64 and then 46. Let's just see how much that changes. And right away, if you look closely here and you remember the things that I've been telling you, you can see that the model converges much faster. So before it converged at about 14 epochs, but now if we look closely, it converges much earlier, about 9 epochs. And this lines up with what I told you before. When the model is more complex, this leads to a tendency to overfit much faster or converge much faster. So we increase the complexity of our model by increasing the number of neurons in our first hidden layer. So that led to that overfitting and the faster convergence. We can also see that our accuracy still coasts around pretty much 80%. And if we also evaluate on the test set, we can see that pretty much ended at the same spot. So now let's go ahead and reverse what we did. Let's do the opposite. So let's dumb down our model. Let's make it so that let's do 64 like we had for the first hidden layer, and then we'll do 4 for the second hidden layer, and let's see what we get. Now we have a much different looking picture here. So we can see that the loss now doesn't go as low as it did before. You can see that before we saw that it went down to 1 pretty much. Now we can see that it goes down to 1.5, and at around 15 epochs it starts to overfit. And then also for the accuracy for validation, we can see that it barely even reaches 70%. So obviously our network is unable to generalize as well as it did before. And this also hopefully makes sense to you guys. In this case, we made our model less complex by reducing the amount of neurons in our second hidden layer. And we also introduced an information bottleneck. So we're squeezing the information of the first hidden layer into the second hidden layer, and then that has to be extrapolated into our output layer, which is much larger than the previous layer of only 4. That's why we're not getting as good results. And that's pretty much all I wanted to show you guys. I also encourage you guys to play around with the batch size and just keep playing around with the layers itself to see what you can get. Just see how changes actually affect the output. And yeah, hopefully this all made sense. Now you guys should know how to do single label multi-class classification. Hopefully you found this interesting, and thanks for watching, everybody. So that's it for this video, everybody. I really hope you learned something new. If you liked the video, please hit the like button, and if you want to see more, hit that subscribe button. Make sure to also check the description below for important links to code and other resources, but also really important, join our Discord. We have a big community of over 5,000 programmers, and it's a place where you can find new friends or get help on any code that you're stuck on. If you want to support what I do on this channel, please consider hitting the join button below, and this will allow you to support my channel for as low as $1 a month, but there are different tiers to choose from if you want to. For anyone that becomes a member on my channel, you get a special rank on my Discord server, early access to new videos, and you can just see yourself on the screen right now. So if that sounds cool to you, feel free to join. If you don't want to, that's fine. If you can't, that's okay too. I really just appreciate you watching the video anyway. Thank you so much. And that's it. Peace.